In this video in section 13.2, we're going to look at question number 5, which is asking us to sketch the graphs of a few different functions and then to state their domain and range. Okay. Now, the big idea for a problem like this is to use some things we've already seen up to this point. Okay, so looking at this first function for part A, f of xy is 4 minus x squared minus y squared. Okay, if I rewrite this in the following way, this would be 4 minus the quantity x squared plus y squared. Okay, the benefit of doing so is that I have already seen what z equals x squared plus y squared was, right? That was just our circular paraboloid that we looked at in question number 3. Okay, so this thing had a graph that looked something like this. Okay, and we had these circular contours, right? Okay, so now what I can do is just think about the equation for our function, f, right, in terms of applying some graphing transformations to this thing, okay? So here we have z is x squared plus y squared. So if I put a negative in front of the expression, that's just going to, well, flip the bowl over, so to speak. All right, so this would be z is the opposite of x squared plus y squared. And then with the 4, well, that's just going to do what? It's just going to shift us up 4 units. Okay, so putting that all together, I'll go ahead and do the sketch over here. We're going to get a paraboloid now that looks maybe something like this. Okay, and so, all right, this would be our graph of our surface. Okay, and one comment here, this point, right, the vertex of the paraboloid, this would just be located at the point 0, 0, 4 because of the vertical shift. Okay, and then also we can go ahead and state the domain and range. So as far as the domain is concerned, well, the domain, right, are there any restrictions required here? Any potential sort of badness that can happen? The answer, no, right? Any x or y you feed this thing, you're going to get a nice, well-defined output. So here the domain is just all of R2. And then for the range, this is the collection of all outputs z. Now you can think about the range as, say, looking at the projection of our surface onto the z-axis and then asking what portion of the z-axis do we cover? Okay, and from this picture we can see, well, we're going to cover z equal 4 and everything below it. So I could write that as an interval. This would be minus infinity up to 4. And then I'm going to include 4, so you got that bracket. Or if you like, you could write that using set notation. This would be the set of all z's such that z is less than or equal to 4. Okay, great, not too bad. Let's go ahead now and check out part B. Okay, so now we're looking at g of xy is the square root of 4 minus x squared minus y squared. So again, I want to try to fall back on something I've already seen. And so for that, I'm going to go ahead first and write this as z is equal to the positive square root of 4 minus x squared minus y squared. And because of that positive square root, I know that z has to be greater than or equal to 0. Okay, so now I'm going to go ahead and square both sides and rearrange. So this is saying that x squared plus y squared plus z squared is equal to 4. And again, I have this restriction on z. And so this is just a sphere equation, right? The sphere would be centered at the origin and have a radius of 2. But then because of this restriction on z coming from the positive square root, this is just going to describe the top half of that sphere. So this, in fact, is just a hemisphere. Cool, all right, so maybe we're looking at something like this. So maybe there's a cross section, and then here's a cross section, and then these things come together, right? Their contours here would just be circles. So here I'll mix up the color a bit. Here's another contour, so on and so forth. And yeah, the radius here would be 2, right? So this would be 2, 2, and 2 up here. All right, cool. So now let's talk domain and range for this. Here I'll domain would be what? Well, we've looked at a problem really similar to this as well back in question 2 when we looked at domains of functions. Here, notice I can see the domain if I think about just projecting this hemisphere onto the xy plane. Okay, it's going to consist of all points that are on this circle of radius 2, so that base circle, and then everything on the interior. Okay, so here I can say this would be the set of all xy such that I need x squared plus y squared to be less than or equal to 4. Okay, so this would be an entire disk here of radius 2. So it'd be all of this stuff here. Okay, cool. All right, and then for the range, well, for that, right, again, we can think about projecting our surface onto the z-axis, and we're going to cover what? We're going to cover everything from, well, 0 at the low end all the way up to 2. So as an interval, that would just be the interval from 0 to 2. Or if you like, you could write that as an interval, sorry, as a set, and say the set of all z such that z is greater than or equal to 0 and less than or equal to 2. Okay. All right, well, very cool. So now let's go ahead and look at the last one here. This is the function h of xy is 4 minus x minus 2y. Okay, now here, this is a linear function. A linear function of 2 variables. And so for that, okay, we know it's going to describe a plane in 3-dimensional space, okay? So to just quickly sketch this plane, okay, what I'm going to go ahead and do is just find the x-intercept, the y-intercept, and the z-intercept. So for example, if I look at where, say, y is 0 and z is 0, then that would be what? It would be x is equal to, so I'm setting y to 0 and z to 0, which is really just our h, and so that looks like x is going to have to be 4. If I, so go ahead and put that over here, say at 4. If I set, say, let's say x to 0 and z to 0, then y would have to be what? Well, here I'd get 0 on the left, and then x is 0 as well, so 4 minus 2y is 0, so y would have to be 2. So this would be, say, like about right here. And then finally, if I set x and y to both be 0, then my z coordinate would have to be what? Well, if these are both 0, then z would just simply equal 4. So that's going to be, say, up here. Okay, so what I know, right, is I'm describing a plane, and it's a plane, right, that passes through these 3 points. So for the moment, to draw the portion of the plane in, say, just the first octant, right, where x, y, and z are non-negative, I would be looking at this picture here. So I'll go ahead and label these points 0, 0, 4, 0, 2, 0, and 4, 0, 0. Okay, but of course, this plane really does extend indefinitely, so I'm going to go ahead and just kind of draw these dashed lines here, right? The plane doesn't cut off, but I'm just sort of highlighting, right, the portion of the plane in the first octant there. Okay, cool. So now let's go ahead and talk domain and range. So for our domain, well, certainly no restrictions here to be made, so this would be all of R2 again, just like part A. For the range, well, if I were to project my plane onto the z-axis, since this extends indefinitely, right, and becomes infinitely large in the positive and negative directions, our range, in fact, would be all of the real line, right? We cover the entire z-axis. So there I can just say that the range is R, okay? All right, well, very good. That's going to do it for this problem.